Hello, and this is the second part of Unit 12. This is actually the last slide I showed in Unit 1 with regional productivity, where we talked about phytoplankton numbers and zooplankton numbers in terms of the seasons of the year and being more productive in the spring and summer, probably no surprise, and less productive winter and fall. Having to do with thermocline, whether it be low latitudes, mid latitudes, or high latitudes. Tropical ocean productivity is very low. We have nice warm water. We have the ability to have lots of immature plankton, which could actually hatch out of eggs. They're going worldwide, and if they actually do hatch, they're going to find themselves in a very nutrient poor level. And that's probably because this really thick thermocline forms where we get the warm water and the cold water, and we get a very large temperature change, and the two water masses don't want to mix. Reason we don't get a whole lot of life down here is because it's also in the aphotic zone, so there's not a lot of life. So there are critters that live down here, but just not a very large amount of biomass. It's all because of the strong thermocline, and it inhibits the thermal mixing. And the same thing, low latitudes actually have a nice thermocline. Mid latitudes have a nice thermocline in the summer, but not so much in the winter. And polar, cold almost all the way down, almost no thermocline, really good mixing, and why the cold water is again really good for critters. Tropical high, you do get some places where you do get blooms in biologics. Can happen with equatorial upwelling, where we get northern winds coming this way out of the northern hemisphere, southern winds coming out of the southern hemisphere, and they actually cause the Ekman current to go in a 90-degree angle, and that actually pulls away, and that allows water to move up from below, and does make the equatorial waters fairly nice for critters, a nice place to grow. And then you also have coastal upwelling, where you get the wind blowing down and pushing water out, pulling moisture up, or pulling water up from the low areas, called coastal upwelling. And you can see there's the benefits of the equatorial, there's the benefits of the coastal. And again, we have high numbers being in the reds, the yellows, lower numbers, greens, blues, and purples. So we've got large areas of the ocean almost like a desert, and we have some equatorial and polar areas that are beneficial because of the upwelling. Temperate oceans, we have a very good thermocline, strong seasonal component. So we get, if you take a look at it in summer, we get lots of sunshine. Our numbers go down because the microscopic algae and the grazers, the phytoplankton numbers blossom in the spring. They wane in the summer, and the nutrients go back up. And as the nutrients go back up and the waters start to warm, the populations grow again. Have low level sun during the winter, and that actually allows the thermocline to get higher. And then higher levels with spring, summer, and fall, that allows the thermocline to drop down a little bit and set up so much more strong, much more strengthened thermocline, less mixing. So the winter in mid latitudes, we actually do get a little bit more biologics than we do in the spring, certainly not in the summer, and then back in the fall. All has to do with the nutrient supply and the amount of sunlight. Energy flow in the marine environment as well as terrestrial environments is one directional. Sunlight lights up the planet. Producers pull in some of that sunlight. They're called autotrophs because they make their own energy. Consumers have to eat other critters. They're called heterotrophs, other energy. They'll eat producers. They'll also eat other heterotrophs. So we have herbivores, which are eating the producers. We have carnivores, which will eat heterotrophs. And if you're a fish eater, you're called a piscivore. Autotrophs, actually the green stuff in the water and the down here. Then we have consumer herbivore, this manatee. We have piscivores, carnivores, this dolphin. And then we have omnivores, like this turtle, who will eat plant matter as well as fish and other things. And then what rounds it up are the decomposers. They're also a form of heterotroph, and they'll consume anything above, but once it's dead. Energy flow, one direction. Radiant energy comes down. The plants take in radiant energy, they take in carbon dioxide and water, and they make sugar, so they actually make a chemical energy. And that chemical energy can be ingested by animals and that can be released as heat energy and mechanical energy. So the chemical energy goes in, and then we expend muscle energy, whether it be the heart, the muscles, the lungs, the gills, the whatever. We also heat up the water, and that allows more entropy. Entropy is basically the mixing of everything. So low entropy if things are separate, and then high entropy if the things are in there. And that fish is going to try to heat up this water. So the water doesn't really organize the energy where the fish did and the plant did. And even when the fish dies, it goes in there, and that's going to actually release entropy because these things break down and get released back into the environment. We have things called symbiosis. Symbiosis are two critters living together. We can do it commensalism, where we basically get one organism benefiting and the other one not so much, or actually has no effect whatsoever. And if you can look at these two critters, one of these benefits, probably not the shark. These fish benefit by swimming next to the fish. The shark doesn't benefit at all. Mutualism, where they both benefit. This clownfish, Nemo, living in the sea urchin. The clownfish can actually dip into the sea urchin, and they do feel the stings, but they've got a mucous membrane around, so they minimize that sting. So they go down. They can get protected by being in this sting zone, which other fish want to stay away, and they'll also keep some of the smaller predators away that will nibble on the sea urchin. And then we have what's called parasitism. You can see this poor fish has got some nematodes actually growing through the scale of the fish and actually sucking out the blood. So one benefits, the other one's harmed. And all these things give rise to cleaning stations, which happen all over the ocean, where critters can come in there and fish will come in and actually pull the parasites off them. So that this fish could benefit in this picture by going over, and these nematodes would actually be fish for these, or food for these other fish. So the cleaning stations do help out. The problem is if that turtle actually likes this kind of a fish, how does the fish actually know to go there? And apparently they've worked out some sort of system that even if this shark actually goes to a cleaning station, fish will come out and actually clean all the parasites on the outside of this fish and not have to worry about the shark turning around and eating them, at least not at that one time. Biochemical cycling, matter is always cycled, but it always goes from one direction to another. We can have plants producing energy, and they can be eaten by other creatures. Then when they die, they can be decomposed. They can also release waste products, either the plants or the animals can. And then dissolution, where it actually dissolves into the water so it can be utilized. So that's what this picture is sort of showing you. Salt gets into water, and water, actually it's ionic compound. Polar compound actually goes in, and the negative end pulls around the positive ion chlorine, and then the positive comes over around the negative sodium, and it actually moves around and pulls the things out. Then we have three cycles I want to talk about. Carbon cycle, where we actually cycle carbon. Carbon, the purple is the inorganic type, the carbon dioxide. It can be in the water, and the algae, the phytoplankton, the autotrophs can pull the carbon dioxide out, turn it into glucose. That glucose can benefit critters, other critters, animals. They can also benefit fish and eventually humans. And when these guys die, the bacteria will release it. Bacteria can also come in and can be eaten by some of these critters. If you take a look, the algae can die and release the carbon back into the environment, where bacteria will take it and actually fixate it back into carbon dioxide. The dead phytoplankton down, dead algae can be eaten. Dead algae can go all the way down, so we have the organic compounds, basically glucose, and then we have the inorganic, basically carbon dioxide. Also have the nitrogen cycle, and again we have inorganic and we have organic. We have organic and inorganic. Nitrogen in the atmosphere, 79% of the nitrogen. 79% of our atmosphere is made of nitrogen, but it's absolutely useless for life until it gets to this nitrogen fixing bacteria. They'll pull the nitrogen out of the air and they'll fix it either as nitrate, nitrite, or ammonia nitrogen, and that can be utilized by the autotrophs, and the autotrophs can actually give that up to the protists. Protists can die and release it back into the bacteria. The phytoplankton can die, release it back into the bacteria. Exhalates and mutulates. Exhalate is a liquid given off by, and mutulate is solid material, broken material given off by. They can go this way, and then you can have the phytoplankton or the bacteria actually go into the protists, which we talked about before. And then some of this nitrate can move into nitrous oxides and go into denitrifying bacteria, where we actually turn it right back into molecular nitrogen. So it gets cycled through life. And the last one is phosphorus. Phosphorus is something that used to be in laundry detergent. We found out that the laundry detergent got into the biosphere and actually made the bacteria levels go crazy, and that actually pulled water or oxygen out of the water, and we had lots of death. And again, we have the organic phosphates and we have the inorganic phosphates. Inorganic phosphates usually in rock. Weathering and erosion releases that into water, and that can move up to usable phosphates, so the algae can pull it out, and then the algae, of course, can give it to the zooplankton, and zooplankton can give it to the fish, and the fish can give it to the humans or whatever. All of them have waste products that go to the bacteria. And you can have the animals like guano and bone material actually turning right back into the rock. So basic things with all these cycles, you can go start at any one of these locations and you can end up in another. Trophic levels, these are feeding relationships. It's a very inefficient system where we have about 10% of one level's energy going to the next, and we have 90% loss per level. So if we have 10,000 units in phytoplankton, if that actually goes over to the herbivores, mass eaten by the herbivores, and that we only have 1,000 units of energy, and that's eaten by different herbivores, and that's only 100 units, and that goes to growth and reproduction, and that's eaten by carnivores, and we lose 90% of the units. So the energy goes from 10,000 down to one unit. So we lost 9,999 units going all the way to these carnivores, and that's because we lose in feces, we lose in respiration, and we die. So all the energy goes out. So we have a 10% energy gain and a 90% energy loss per unit. That gives rise to things called food chains, where we actually take diatoms or flagellates and we move those over to mollusk larvae, like clam larvae, and that can go up to the North Sea herring. We can also have the diatoms going into that mollusk larva and going to arrowworms to the herring. We can have it go to copepods to arrowworms to herring, copepods to sand eels. We can have it just keep going through this whole section all the way through. So we have lots of chains, and it's much easier to start talking about it as being a food web. Basically, the energy goes from lots of different levels to the top level. This is a 3-level food chain. The northern herring, and it's actually the food web of the northern herring. The biggest change we have is going from 1, 2 to 3 rather than 1 to 2. And every time we go, like we go to the diatoms to the copepods here, we lose 90% of the energy. So 1 pound becomes 1/10 of a pound, and that actually goes to here and becomes 1/100th of a pound. So we lose a lot of energy as we go up. It can also be called the biomass energy pyramid, where that 10% rule, or 10% goes from one level to the next, where we get 90% loss. If you take a look at it, we're all going to go up to this 10,000 kilogram killer whale. Killer whales can weigh well over a ton, and maybe multiple tons, up to 5 tons. And if we take a look at that, it all starts down here with phytoplankton. Phytoplankton, the producer. You need 10,000 times the mass of this than this to feed it. And basically it's because we lose 90% of it going to phytoplankton. So we need 1,000 times the mass of the killer whale of this to make the killer whale. And then we lose 90% up to the small fish, the anchovies, primary carnivores, and that's going to be 100 times the mass of the killer whale. And we go up to the bonita, which is the secondary consumer, where it's 10 times the mass of the whale, and then we have the killer whale, which is 1 times the mass of the killer whale. So you can start with 10,000 times the mass and lose 90%, lose 90%, lose 90%, lose 90%. So it's not a very effective level to actually be the fifth order or the tertiary, the fifth order consumer in here. So we would really like the killer whale to go down and eat phytoplankton, because then it only has to be the 10 times the mass of the killer whale. And then if we actually ate killer whale, then that we lose 90% of that too. But we don't eat killer whale. We do eat bonita. This is a form of tuna, and we eat anchovies, and we eat phytoplankton and zooplankton. Although we don't know it, but it's mixed in with a lot of our food. Microbes, we have microbes in the ocean. These also consume the primary production, so they'll actually eat the plant material. They'll also eat the liquids given off by plankton, the exhalates, and the solids given off by plankton, the mucilates. And the zooplankton excretions, they'll eat blue-green algae known as cyanobacteria, and they'll actually eat viruses, parasitic viruses. And the parasitic viruses can actually cause problems to all these levels too. Last slide, bacteria and bacteriophage. We have bacteria living in the ocean, and they do their job really well, but we do have viruses out in the ocean which will actually hunt out the bacteria. And what the virus does is it actually injects its DNA into the bacteria, and instead of the bacteria, which has a ring type DNA molecule, instead of the bacteria actually making bacteria, it actually makes new viruses, and eventually the bacteria will break out open and release thousands, maybe even tens of thousands of viruses, which will go out and infect the rest of the bacteria. Give you some idea of the size. These are diatoms, which are smaller than what you can see with your eye, and these are the bacteria. And then we have iron molecules, and we have carbon molecules, and we have vitamin molecules out there, all being very small. So it gives you some idea of the size of what we're talking about. And that is the end of Unit 14, Biological Productivity and Energy Transfer, and this is the first unit. I'm hoping that I can get through to get you guys set up for your oceanography final year project, where you guys are going to come up with different ecosystems, but you're going to have to talk about the energy transfer, the production of the energy, and the energy transfer from one level to the next. Okay, thanks for stopping by.